right, welcome everybody. So we're at lecture 11, and we're going to talk about non-zero mean stress. So this is very common in mechanical components to have a mean stress that is not zero. So it could be positive. We could be operating in a mostly tensile mode. Could be compressive. We're operating mostly under compression. And so we'll learn one way to deal with that. We ended the last lecture talking about these factors that can modify the endurance limit or the fatigue strength. And I kind of talked to you a lot about the reasons for them, right? So where do they come from? What does it do to the SN curves? But, you know, we could have 100 SN curves and sort of have to sort through them all. Or we could use the more aggregated data to help us apply these factors. So if you recall, we had an endurance limit, I'll call it, for our part, which was a product of a bunch of factors, right? They were all K's, and it was like A through E times our endurance limit as determined by the R more fully reversing bending fatigue tester. And these factors are called Marin factors. And so I'll just go briefly through what is the range of those, right? So how much do each of these really matter? And I'm just going to cover this briefly. And if you need to apply these for like a homework problem or according to some system you're trying to analyze, it's really helpful to kind of just look things up on charts, but I wanted to give you at least the range of how much they affect things. So the first one is the surface factor. And we said last time that all of these factors are below 1, okay? So they reduce the endurance limit. They give us a lower stress by that which we have to stay underneath on our component to have an infinite life. You can apply these also to other fatigue stresses that are not under the endurance limit, and it's just going to sort of decrease whatever the fatigue strength is at some number of cycles that you're trying to aim for. It just drops it down. So for the surface factor, I'm going to put a plot here, and the y-axis is going to be that surface factor. And this one is the one with, I think, the broadest range. So actually going to go like 0 up to 1.0, so the whole range. There's no surface that actually drops your endurance limit down to 0. That wouldn't make a lot of sense. But there are surface finishes that could drop your endurance limit precipitously. And so one of those is just sort of the more crude finishing method of a forged surface, right? It's kind of as forged. There's no other finishing operation. So those surfaces are left pretty rough. And I'm going to go with like, this kind of hits this axis at like 0.55. And then there's a y-axis to this plot, or sorry, there's an x-axis. So the x-axis to this plot is the strength of the material that we're working with. So ultimate strength and tension, SUT, we've been working with that one. And this axis goes from something like 70 kpsi up to about 250 kpsi. So the stronger the material, the more it's affected by the surface. So that means our Ka is going to drop for stronger materials. And so this is why it goes down, the plot goes down so far. All right, so it kind of goes down something like this. And so the lowest you could really ever have is something like 0.2. When we go up now, here I'll draw a horizontal line across the top to kind of bound the plot. Let's go the opposite extreme. Let's say we have a perfectly polished surface. And I'm talking about like metallography sample polished, right? So almost perfectly flat. And that would be basically that top line that I just drew to bound the plot. We have no change, and it's not a function of how tough the material is. Okay. So I'm going to go highly polished. So great, if we don't want this surface factor to drop our endurance limit, we just have to pay a lot more to get the part finished appropriately. If you have a ground finish, which is a little bit more common, you can get about 0.9. Come on, pen, there we go. You can get about 0.9 for the lower strength materials. And then as you get to higher strength materials, it drops off a little bit, but not much. So that's a good. And then if you machine a part, it has almost a linear relationship, and it starts at about 0.8 and goes down to 0.5-ish. So I'm just going to draw kind of as straight a line as I can. Machined. That's an M. Okay. So that's pretty typical, right? Machining is what you do to sort of take your part from a roughly formed part, like forging, rolling, then you machine it into the desired geometry, and then you could add more finishing processes, right? But if you leave it at the finish that you machined it at, then your surface factor is going to be somewhere between 0.8 and 0.5. So this is the one that has really the most effect. And there are models where people try to put some power law to fit this decrement, but it's not really necessary because these factors, if we're trying to estimate between, 0.5 and 1, then it really is an estimation. So that's the surface factor. And I'll provide these charts that I'm giving as kind of like supplemental material from the textbook that I pulled them from. It's the textbook we use for Mech 1 EML5005, so that you can have that as a reference as well. The next one, KB, is a size factor. Okay. And so it's been observed that the endurance limit in bending and torsion decreases slightly with the increasing size of the component. And this has been observed to happen or thought to happen not because of something inherent, happens when the component gets larger, other than its surface area increases. And so the amount of material that you have on the surface that could be experiencing a higher stress state is higher. So that's all that it really comes from. And so we define KB by some equations based on the size range. So I will give 2 equations, and I'm just going to give them in English units for now. So if we have, I'll write this over here. So most of these are going to be rotating shafts or round shafts. So if your shaft is less than 2 inches in diameter, so on the smaller end, then you have a KB factor of whatever that diameter is divided by about 1/3, and then to a power of minus 0.107. So you can tell that these are empirical equations. They came from experiments because they have these exponents that are not whole numbers. And then if the shaft is bigger, kind of up to about 10 inches, so this is going up into much heavier machinery, then this factor is approximated by 0.91 times d to the minus 1.157. And so we could plot this, but it's just an approximation. These typically fall also between kind of 0.6 and 1. So if you want to keep the endurance limit higher, keep the shaft size below 2 inches. The next one is a loading factor, Kc. And if the specimen is in bending, so this is also going to be different values for different cases. So if it's in bending, then our factor is actually unchanged. Like it doesn't change the endurance limit at all. Okay? And this is because the curves that were first generated that we always are going to go back to, these SN curves or SNP curves, were generated in a rotating bending test. So we don't have any change from that. If we do the same, or if people do the same experiment with other types of loading, let's say pure axial loading, then the endurance limit in bending is found to be about 15% lower. So if we do have axial loading, we might drop that and use a lower factor there. And if we have the experiment done in torsion, they found that they get almost 40% decrease. So we need to compensate for that by this loading factor. Okay. I'll keep going on this slide because these don't take up very much room. Kd is a temperature factor. And this can be thought of as not just sort of a temperature factor, we don't know where it comes from, but what happens is as the temperature goes up, the material has that recovery, right, at the nanoscale, and its ultimate strength and its yield strength drop off. So we can say that for, oh, I didn't write this down here. For temperatures about 400 C and below, it doesn't matter that much. So we can just say that there's no need to compensate for temperature. Just write that here, no need. But if temperature is greater than that, then we might see some of those effects. And so we would say that this temperature factor is a factor applied to the, what can I say, the endurance, a factor applied to the, how those properties are changing compared to room temperature. So we take whatever's happening at room temperature and then multiply it times something. And it's a function of the temperature. So I'm just going to write the equation here. So it's kind of this factor of at temperature divided by room temperature, and it's a function of the temperature itself. So one approximation is about 1 plus whatever the temperature is in degrees C times a factor. I'm going to run out of space quickly here. So I'm going to go to the next slide and finish writing this equation. So Kd equal to the condition compared to room temperature. So it's 0.99 plus Tc times 5.9 times 10 to the minus 4 plus, actually that's a minus Tc times 2.1 times 10 to the minus 6. And the Tc is squared there. So it's a second order equation there. Okay. Just of note, this is for compensating for temperature if you only have experimental curves that you're looking at or data that was taken at room temperature. If you somehow magically have curves for your exact material, these SNP curves taken at a high temperature, then you don't have to compensate for temperature after the fact. So only compensate one time. And then the last factor is that reliability factor. So if we want to have very high reliability, then we want to go below our sort of average of the SN curves. And so it's going to drop the endurance limit down. And if we want to go to, these are just taken from those normal distributions. So if we want to go sort of 99.9% reliability, then we're going to have KE equal to 0.753. So we lose about 25%. Let's say 99% reliability, that's about 0.814. I'm just going to draw two more here. 90% would be 0.897. And if we're right in the middle, right, 50% reliability, then we don't modify it at all, because that's the definition of this reliability factor. Right? If we're at the middle of the distribution, then that's fine. So oftentimes we want to be above 50%, so that's going to drop the reliability factors. So one exercise that I have my students do in EML5005 is I have them look at all these charts and these ranges, and I say, calculate the worst possible case scenario, right? So you're basically multiplying like 0.1 for Ka. Let me just go back here. Yeah, like 0.1 or 0.2 for Ka, and then maybe 0.5 for Kb. And then you keep going down from there. You're in torsion, so then you're at 0.6. You're at high temperature, so now you're 0.5. And then high reliability, 0.7. And so you really drop your endurance limit exceedingly low, right? And you can also do the same thing for, you know, what's the highest value I can get? Well, the highest value is 1. Our endurance limit is unchanged. But the amount of money that would have to be spent to make the component have an endurance limit modification of 1 would be significant and probably not worth the payoff for whatever the operational component is. So I gave you these factors to try to estimate sort of from all of the different empirical curves. We have SNP curves. And so how do we then, what's the procedure if we want to do some design to avoid high cycle fatigue? High cycle fatigue. Whoa, hold on, can't spell today. Well, the basic overview is choose a material. And then find the most sophisticated set of these SNP curves you can for that material. That may be just room temperature, RR more data. It might be something more sophisticated from maybe a handbook, right? So the Machinery's Design Handbook will have a lot of these. And so you find kind of the best set of curves that you can. And then you start thinking about your component. And if you don't have fully reversed zero mean stress loading, then you have to compensate for that non-zero mean stress. And that's what we are going to, that's what we're going to dig into a little bit more today. And then finally, you apply those modification factors. And then you see, okay, if I have to withstand X amount of stress back on the SNP curves after those two things, what is the size of some component that I need? And so we'll try to get to this example of a rotating shaft today, where we're given constraints, and then we sort of go through this, maybe not the third one, but we go through at least the second one, which is accounting for the non-zero mean stresses. Okay. And then the book is very wise here. It states at the end of these general procedures that these are used for analysis, right, and sort of prediction. But before putting something into operation, it is, quote, always advisable to subject the final design to full-scale prototype testing under simulated service conditions. Okay, so lest you use this and then move forward without any full-scale testing. And you may have to iterate through this. You may choose a material and then find that you can't possibly support the stress that you need to with that material. You may have to go back to the drawing board. Or you may find that you can get a cheaper material, that you've actually over-designed this. And so you can go back and choose a lower strength material for your application. But this is the general procedure. So you just to be totally clear, you wouldn't apply those modification factors to some stress, some effective stress, if you did not already compensate for the non-zero mean stress, right? So just try not to get these like out of order. Okay, so now let's talk about the influence of non-zero mean stress. Whoop, I'm gonna have to come back to that. Okay, so I'm gonna draw a plot of empirical data, and it's gonna be on a plot where the x-axis is the mean stress. Okay, so we talked about zero mean stress, right? That would be here at the origin. Or anywhere along that vertical axis. And so this way is compressive mean stress, right? Sigma m less than 0. And the other way is tensile. And then the y-axis is the stress amplitude. Okay? Because that's what we look at on these fully reversed SNP curves. We look at the stress amplitude. So we have to find a way to combine these two into some sort of design criteria that gives us something called sigma n, okay? And sigma n is going to be defined as the fatigue strength at n cycles on the SNP curves. So that's kind of what we need to find. And so if we look at some experimental data, we can say sigma n here. So that is, and that n could be 10 to the 4th cycles, 10 to the 5th, 10 to the 6th, anywhere in between there. And so in a tensile mode, if we have zero mean stress, that is the condition of our RR more. So we have some data points that are right there on that axis. Okay, but if we slowly increase the mean stress to a tensile mean stress, so if I draw like sort of my stress in time, right, if I go up and I've got a positive mean stress here, that's the situation we're talking about. And as we increase the mean stress, the amplitude that we can use to get the same life goes down. And it goes down, and it's not exact, but it sort of hits this axis at the ultimate tensile strength. Call it like sigma u or sigma ut. But if we do the same thing in compression with a non-zero mean stress that is negative, we don't find the exact same trend. Okay, we find something like this. And eventually, we'll get to sort of minus sigma u. Right. And so this kind of goes back to when we were talking about those static failure theories, where we talked about the energy density, and how if we have a hydrostatic stress, right, then that thing is much more robust to yielding than if we have then the additional energy to distort it, right? And so this is kind of speaking to that asymmetry of fatigue occurring more and more extreme if there's a tensile non-zero mean stress than a compressive one. So one thing that we can do to combine these is we can think about those metrics that we defined before based on the curve. So before we had, I'm just going to go back and draw these one more time. So let's say here's our example stress versus time curve. We had defined R as a stress ratio. Which was sigma min over sigma max, where sigma min is this point here, sigma max is here. And then we also had an amplitude ratio, which was the amplitude, stress amplitude sigma A, divided by the mean stress. And if we plug some things in, we can also find that can be written as a function of the stress ratio like this. So for the example curve that I've drawn here, mean stress is tensile. It's this dashed line up here. And then sigma A is the difference between the maximum and the mean, right? That's the amplitude. Or you can also say sigma A is the difference between the mean and the min. Okay? So these are just basic definitions that we had before. So if we look at this sort of data that I just put up here, the stress ratio is going to be less than 0. And you can see that because the minimum stress is below my 0 on the plot that I drew, right? So if minimum stress is negative and maximum stress is positive, R is less than 0. And then we can think about the amplitude ratio, the same thing. So I drew my mean stress here in kind of a way where if I just look at it by eye, I would say that the mean stress is less than the stress amplitude. Like this is just sort of generalizing here. So if the mean stress is less than the stress amplitude, my A is going to be, I don't know, slightly greater than 1. Something like that. Okay, so the reason that we're calculating these things is that I'm going to show you a master curve, and we're going to sort of use some lines on there that are lines of constant situation or constant combination of R and A, right? And so that'll allow us terminology to describe the stress fluctuations. All right, so I'm going to show you a chart. I sort of passed by it briefly, and it's called a master diagram. And so if you are so lucky, then this can be found for a particular material that you're working with. Very rarely in the class will I show a plot like this, but I wanted to put it up here because I think if I tried to draw it, it would just get out of control. So I'm going to highlight a few things on this so that you can understand how to use it. So this entire chart is for AISI 4340 steel. And so if that's the material we're working with, great. Look up the master chart, right? Very common steel alloys. This is figure 7.61 in the textbook if you want to come back to this later and look at it or open it up. Okay, so it's got a lot of lines on here. So first let's look at the axes. So the x-axis is the minimum stress. So if we write that symbolically, that's sigma min. Y-axis is maximum stress. So we know when we're thinking about the metrics that we just talked about, R is sigma min divided by sigma max. right? So it's kind of the inverse of a slope, okay? And so if we look along the top, we'll see that there's a bunch of R's here. So I'm going to circle this, if my pen will work. So this condition on the sort of the y-axis right there is R equals -1, okay? So we had an R that was also negative. So we'll be looking at one of those lines over here, if that represents the curve that I had before. And then if we go up and along the top, then R goes from -1, it goes up all the way up and around to 1.0 at the opposite extreme up at the top, okay? And so we could follow all of these values or these locations around the top down to the 0 point, right? And that would, if we knew what R was, we could just sort of follow those lines and see, then look over at what is our allowable alternating stress and mean stress for different lifetimes. And so that's one way to look at this chart. If you know your max and min. Another way to use it would just be to put the data points on there. So let me go and get a different color here. So let's say we had a minimum stress, sort of how I drew it on the last slide. Let's go like -40, right? So I'm going to draw that, I'm going to circle it on the x-axis here, -40. And then my maximum stress was higher than that. Let me go back to the chart so I can just estimate. Oops. Okay, so if my sigma min, let's call it 40 kpsi. So it's about 3 times higher than that, so maybe my sigma max is like 120. Okay. So then that's on our y-axis here. Okay. So if I go and I find the point where these intersect, so I'll go up on 40, over on 120. I find myself at this giant purple circle in the center here, right? And so then I can look at the lines that that's on, and that'll help me define the system without having to do a lot of extra work. I can look at the line between the periphery and 0 to find if I care about what R is and what A is. So R -0.4, A 2.3. Okay, awesome. That's kind of the ranges that I thought I had before. And then what I do if I want to know what's the alternating stress, and I'm too lazy to simply just calculate it, is I can take and do a 90-degree line down to the edge here. So if I draw that 90-degree line, then my alternating stress is, I don't know. Yeah, that makes sense. The alternating stress is about between 80 and 90, maybe 85, right? And then I can also follow the line down to this other bordering axis over here, bless you, and my mean stress is about 40. Okay, so this is kind of like a master diagram. And I didn't point out what we, maybe the most important part, which is the lifetime curves that are on here. So my big purple dot is underneath that top series, right? So normally we want to define the safe and unsafe regions on a plot like this. So this line that I'm going to highlight in red here says 10 to the 4. All right, so that's 10 to the 4. So that's 10,000 cycles of stress. And so I am below that. So if I have that exact stress state in AI-SI 4340 and cyclic stresses, I could expect my sample to last greater than 10,000 cycles, but less than 100,000 cycles, because the curve right below that is 10 to the 5. So I've got between 10 to the 4, 10 to the 5. And I could interpolate or something like that if I wanted to make a better prediction. It's about halfway. And then the curve below that says 10 to the 6 and 10 to the 7. Well, how could you have 10 to the 6 and 10 to the 7 life on that exact curve? Well, steel is a ferrous material. It has an endurance limit. And so it's not just 10 to the 7, it's 10 to the 8, 10 to the 9, whatever, right? Because anything we define as 10 to the 6 or higher is infinite life. So if I had this stress fluctuation. I said, okay, this is all right, but I really need to get at least 100,000 rotations out of this. Then I need to choose a state of stress somewhere underneath that line. And if I do that, then I would expect everything to be good. So this is one way to compensate for non-zero mean stress. You find this master diagram and you go for it and you're good. Because once you get the alternating stress, then you go back to your, it should match up with the SN curves, the SNP curves for that material, right? So this is kind of like an expanded SNP curve here, where you don't actually have to calculate and get back to it because it's already built in here. If you know the minimum stress, maximum, or if you just know the other values. And so you can kind of move around this chart to really work with a design problem. You'll notice that it's also asymmetric, and that's because of the data that I put on the prior plot, where if you have a compressive mean stress, it affects, hang on, let me look at this. Mean stress, alternating stress. I lied. This diagram is only for tensile mean stresses. So there's only, if you look at this mean stress line going up on the right side, the mean stresses are only positive. So this is actually just for positive mean stresses going to zero. So this actually doesn't include the negative mean stresses. Because if it's going to, this is a more extreme case. Yeah, okay. So if you don't have the master curve for your exact material, then you have to do something different. So if we are in a data poor situation, then we can only look things up like what is the ultimate tensile strength, right? SUT. What is the yield strength, right? And then what is the SNP curve? And then we can also know for our situation, like what is the amplitude and what is the mean. Okay. So if this is what we're working with and we really don't have anything else to go from, we have to use a relationship in order to go between these things such that we can get back to the SNP curve and our sigma n, right? Our fatigue strength at n cycles. One common way to do that is to follow Mr. Goodman, who proposed a linear relationship between these. And so he looked at all of the data, and he said we can propose a linear relationship and move forward from there. It is a little bit more conservative in the same way as our failure envelopes for the different failure theories, because it's a linear relationship, but it is probably the most commonly used one. So the equation for that is given in the book as equation 7.1, and it states that the stress amplitude divided by the fatigue strength at some number of cycles plus the mean stress, sigma m, divided by the ultimate tensile strength is equal to 1. So these all add up to 1. Okay. And the reason that this is called linear is going back to that same plot that we made before, where we had the mean stress on the x-axis, the alternating stress or stress amplitude on the y-axis. And so we kind of had before come on, pen. All right, one moment. All right, temporarily saved. So we had a data point here, and then we had points that went down like this. And I said they roughly approach the ultimate strength. So let's just normalize the x-axis by the ultimate strength. And I said it started on this y-axis at the fatigue strength, sigma n. So we'll normalize the y-axis by that one. And then we just go between 1 and 1, right? So then we have 1, and we draw a line between them. And that's the Goodman relationship. And we assume, even though it's not 100% true for compressive, if we drew it symmetric, well, that's mostly symmetric, then that's what it would look like. So this is exactly where this equation comes from. Just drawing a line between those 2 points, normalizing them. So anywhere in the middle there, they have to add up to 1 because it's just a ratio of those 2. So inside is the safe zone. Outside is the unsafe zone. There are other relationships that can be fit to the experimental data and to modify it, make it more conservative, less linear, and sort of more rounded. And so those relationships are given in the book if you want to look at them. But really, we're just learning the procedure here. Okay, so this is helpful, but we did have some asymmetries when it came to the compressive side. So to deal with that, so compressive mean stress, right? We need to modify this. So we're going to use the modified Goodman criterion to do that. That's my 5-minute bell. And so we're going to draw an envelope, and it's going to be similar to this, but we're going to draw an envelope similar as we did to failure envelopes. And then if we are inside of that envelope, then we'll last at least the number of cycles. If we're on the edges of the envelope, we're predicted to last exactly some number of cycles. And if we're outside of it, it won't last as long. Okay, so I'm going to go here to the next slide. So I'm going to draw for you figure 7.63 in the text. And I'm going to draw it like this, right in the middle. And the x-axis is going to be the same as we have been drawing. That's our mean stress. And the y-axis, we're going to plot the stress amplitude sigma A. And then we're also going to plot sigma max and sigma min that are going to define an envelope for us. Okay. So we can start with just some like anchoring magnitudes on here. So at the top of sigma A, right, and this is actually kind of the top of both of these axes, we're going to have the ultimate strength. So sigma UT, right? Nothing can go above that stress. And then if this is a 1-to-1, I can draw that on the x-axis as well and label it. So that's our ultimate tensile strength. And then going down from there would be the yield point. So I'm going to write sigma ys. Do that on both axes. Right, so that's the yield point. And then every fatigue strength that we get must be below the yield point, right? So if we have cyclic stresses, then the allowable stress at that level is always going to be below the yield stress. So we go a little bit further down, we get sigma n. Okay. So now we're going to use these values to kind of start drawing our envelope. For this plot, it is for some specific number of cycles. So n is a constant. So we'll draw an envelope for just that number of cycles. All right, so we'll start with the sigma n, right here. And we'll sort of note that the Goodman criterion was like kind of this line right here, or exactly that line right there. So it went from the fatigue strength on the y-axis down to the ultimate tensile strength on the x-axis. And so if we have a, let's just look at the origin first. So if the mean stress is 0, right, so that'd be right in the middle. I'm going to change colors now. If the mean stress is 0, then the maximum, the sigma max that we could get is sigma n. That's from the RR Moore curve. And the minimum we could get for sigma min, right, would be the opposite of that. Draw minus sigma n here. So at these locations, this will be our sigma min and sigma max envelope. This is fully reversing, right? So it's the same positive and negative. So this is the window for a 0 mean stress. So how do we start drawing now the window for other, and the mean is here, right in between the two. So now let's start drawing it for some other situations. So what if our mean stress, if we think about where it is on the y-axis and the x-axis, right, it would be a 1-to-1, right? So I've drawn 1-to-1 kind of in a funny way here, but just draw it like this, right? So that's our 1-to-1 line. That's our sigma mean line for the window. If our mean stress goes up, then our tensile stress goes up as well, or our sigma max and sigma min go up as well, and they follow a window around that line. And so that's what that's going to help us there. Okay. So now let's think about this sigma max. Right? We go back to the definition. That's the amplitude, stress amplitude, plus the mean stress. So our dashed line there is the mean stress, and our max would be the stress amplitude from going along with that. And so what I'm going to do is I'm going to take and go up to here, up to the ultimate strength, and I'm going to draw a line like this. So you can't use that whole line, but we can use part of it below the yield strength. And then we'll do the same. And then we'll do the same thing for sigma min. Sigma m minus sigma a. And so I'm going to take and go from this bottom line here, and I'm going to draw the same and go all the way up. Oops, it's kind of curved line. So you can see now that the mean line falls directly between the other two. So this is now our window of min and max, some sort of stress amplitude. It's the beginning of our envelope. All right, unfortunately, lecture time is over. For the first lecture, so we'll stop here, and let's say we'll take like a 5-minute break, and then we'll come back and we'll do the second lecture where we'll continue with this and then do a numerical example.